would ask you, please note all the gaps which have occurred so far. And in this afternoon, so far in the tutorial, we're just filling the gap from almost the most elementary things until coming to this lecture. And now we're starting to enter the lecture with all the background material you need in order to understand. So please take notes, ask questions, or really just note down questions you have, because you will forget them, and I will too. So in order to ask the questions actually you have concerning the lecture. So what are the different paths which were absolutely unclear, what is good, what is bad, etc. So some feedback is also very helpful. All right, so today we're going to make essentially two things. The first thing is we will write down the very last limit theorem we need, and this is the last limit theorem, which makes sense because we have introduced the concept of infinite divisibility of distributions, and this limit theorem tells us that whenever we have some independent centered normalized null array, and whenever it converges, whenever the row sums converge, then we are in front of an infinitely divisible distribution. This means it's not necessarily the case that we can determine, well, except for some special cases. In general, we cannot determine to which one it converges, but we know whenever there is something like this, and if it converges, then we are in front of an infinitely divisible distribution. And the second thing, and this will be the larger part of the class, is we'll introduce Lévy processes. Well, finally, we'll introduce Lévy processes. First of all, we'll look at examples. The typical examples are, of course, the Wiener process, so Brownian motion, what it is, how it looks like, basic properties, and the compound Poisson process. Well, first of all, the Poisson process, and then the compound Poisson process. And we'll see that all of those are Lévy processes. And then we'll talk a little bit about properties, path properties of the Lévy process, how actually realizations look like. So, but in order to understand this, I have to make some preparations. First, we will start with the local limit theorem, which was missing, and it's just the following. It's very, very easy. It's more or less a reformulation what I've been talking about. So, theorem. So, if let x and k, well, first of all n and k in 1 kn. So as I've said, an independent centered null array. Well, null array was an array which is asymptotically negligible. So, okay, just to recall what this was, this centered means that each of those random variables actually, so the array was just, we have the scheme of the numbers of kn's growing, and here in each of the lines we have the random variables for each of the generation n. We have the sums, which are the SNs. Sn is nothing but Sn1 plus x and kn, okay? They are normalized. So first of all, they're independent. So each of those is independent in each of the generations. And they're normalized in the sense that the variance of Sn should be 1. And they're asymptotically negligible. This means that the limit for n to infinity of the sup of the k's, kn, of the probability that xn k is greater than any kind of epsilon. So for any epsilon we have this 0. This means all those arrays converge uniformly in probability to 0 if those sums, the SNs, tend to a limit, if there exists distribution M on, so we are in R, such that the distribution, so L of Sn, or the same thing as Sn, the distribution of Sn tends in distribution, so weakly, towards mu. So we have those sums. So now, well, they can depend on n. So we had also already the examples. For example, these Bernoulli distributions, so the binomial distributions. The Bernoulli distributions for each of the k's, and the sum was this binomial for the Poisson limit theorem, and also the binomials, the recentered binomials for the central limit theorem. So if these kind of things converge, then mu is infinitely divisible. Okay? So this is a theorem which tells us that whenever there's a limit object, it is infinitely divisible. Okay? This is very, very general. It doesn't say it's stable, or it's normal, or it's Poisson. It's infinitely divisible. It can be one of those, and we know already how these infinitely divisible distributions look like. We know how the characteristic functions look like. Please. Oh, okay. Weak convergence. So, okay. Yesterday. Weak convergence says that the expectation of f of Sn converge to, well, if you have a random variable, so, pardon, I would like to write it down in terms of all kinds of moments. So if x is a realization of mu, so it's a random variable with distribution mu, then Sn converges in distribution to x if, or the same thing, so Sn, I'll write the same thing towards mu, if the expectation of f of xn, of Sn, pardon, Sn tends to the expectation f of x for all f bounded and continuous. Okay? So also yesterday in the tutorial I was trying to motivate this. So where this comes from actually is, we would like that if this f were just an indicator function, then we would have the convergence of the probabilities. This means that Sn being in A converges to the probability of x in A. Unfortunately, we're not allowed. Unfortunately, measurable functions are way too restrictive. But we have to take a weaker class, a class which is a little bit smaller, and these are the continuous bounded functions. So if we have an indicator function, it looks like this. Well, okay, it should be 1, 0, and 1 somewhere, and we have the set A here. But we can approximate it like this. Sometimes we can pass to the limit, sometimes we cannot. Okay, so this tells us that essentially all good, the probabilities of all good events do converge. This is the idea. This is weak convergence. This means if we have densities, then the densities will converge. Okay, this is the essential point. So this is the standard convergence. This is the convergence, for example, in the central limit theorem. It's a convergence in the Poisson limit theorem. It's a weaker convergence than, for example, in the law of large numbers. There it can be much stronger. But in general, this is the weakest convergence, which is used typically also for non-mathematicians. Okay, so just to sum up, whenever we have an independent centered normalized area which is asymptotically negligible, and we have the sum, and if the sum converges, the distribution of the sum converges to something, this something is infinitely divisible. And of course, this is one of the basic assumptions. This is much broader than, for example, the theorem by Lindeberg, which tells us that if we have an additional assumptions on the variance, such that the variances actually are negligible, so that we don't have only the probability here, but also the variances are negligible, then it should be, then mu should be normal. But it allows that the variance of single elements here is a little bit, has a contribution on the whole sum. And this is something which is prohibited in the normal regime. Okay, so now comes a certain cut, and I would like to come to Lévy processes. And in the end of the class, I hope I still can write down why infinitely divisible distributions have to do with Lévy processes. In fact, Lévy processes are determined by only each Lévy process, the law, the distribution of a Lévy process is determined by a single infinitely divisible distribution. It's the distribution at time 1 or at any given time t. If we know this, then we know the distribution of the whole Lévy process. This is something I would like to see, hopefully, at the end of the class, such that we can have the bridge from the limit theorem to the distribution of Lévy processes. Oh. First, Lévy processes. So this is the second big chapter. In the beginning, we'll write down an example of a Lévy process. So far, we don't know what a Lévy process is, but we will just carve out the main properties in order to see what the properties of a Lévy process should be. And for this, we look at what is Brownian motion. Brownian motion. A Brownian motion, I will write it BT. BT is a stochastic process on a probability space, omega A P, satisfying the following. So a stochastic process, you can, stochastic process, you can understand a family of random variables with, which are indexed by the parameter t. So far, so good. Which has the following properties. First of all, B0 should be 0, P almost surely. For essentially all omegas, it should be 0. Then we have independent increments. What does it mean? This means for any n in n, and any repartition. So 0 is T0, T1, T2, Tn. We have that the vector of BT1, well, I can write down B0, but BT0, but this is 0. BT2 minus BT1, BT2 minus BT3 minus BT2, just to make it clear, until BTn minus BTn minus 1, that this is an independent vector. So this is a family of independent random variables. So this means those are random variables, and these random variables are independent. So this is a family of independent random variables. The repartition is any repartition. P almost surely. P almost surely. This means there exists an event of probability 1, which I don't specify, such that for all events in this event, all elements in this event, all cases, it is satisfied. Then we have that the stationarity. The stationarity, it tells us that for all 0 less or equal s less than t, we have that the distribution of bt minus bs, this is once again a random variable, has the same distribution as bt minus s. I write down minus b0 for clarity, but this is just 0, is distributed like a normal distribution, 0 t minus s. And just an additional property which is not necessary, actually one can infer this, the paths are almost surely continuous. This means for P almost all omega and omega, we have that the path bt of omega are continuous. So, okay, so what should this mean? So first of all, this is a family of random variables, but it's sometimes convenient to consider this as families of continuous functions which start in 0. So what do we have? We start in 0, and then we have certain families of continuous functions, which do things. They are random, and they're random in the sense that, as I've told you, if we have just a repartition, then the random variable of the increment of this increment, of this increment, of this increment, of this increment, and this increment are independent. So whenever we have come somewhere, we just forget about what has happened so far. So whatever has happened until here, we don't forget it, so it does not enter in the distribution of this increment. And it's stationary. This means the distribution to come from S to T, from here to there. So these are many possible ways. The distribution from here to there has the same law as the distribution to come from 0 till S minus T. And it should be normally distributed. So there are a lot of normal distributions involved there. So each of those is normally distributed. It's a Gaussian process. Okay? So you can understand this as a family of random continuous functions which have a lot of internal properties. This means whatever you look at, whatever kind of partition you're looking at, the increments in the partition are independent. And if you look at an increment, you can always switch it to 0 and you have t minus s. Okay, so coming from here to there is the same thing as going from 0 till t minus s. Is it more or less clear what this object should be? Property 4 is continuity. So each of those paths is another omega. This is omega 1, omega 2. So this is b, so this is a function of omega 5, let's say, b of omega 4, so b of omega 1, let's say. Okay, so these are functions which have the index t, so the argument is t. For each omega, for each omega you can say, you have a continuous function. So this means, this is why we can imagine these random variables as continuous functions. Is this clear? Please. No, not necessarily. No. So this is this repetition is not necessarily, no, not at all. Whenever we have non-overlapping type intervals, then the increments on these different steps are just independent. No, it will not be independent. It's sure. So we have just the same distribution. So this, so the distribution. So we should write it like this. So or equal in distribution. So distribution of this and this is equal, but this does not mean that they're independent. No. Sure. In general, no. Just more questions about this. So this is first of all just a definition. Okay, and the question now is, first of all, does such an object exist? How does it look like? How can we construct it? And this is what I would like to do. I would like to construct Brownian motion with you. And it's, please. Almost surely, exactly. In general, yes. And so there is, of course, there's a theorem. It's called the Kolmogorov-Chertsov theorem, which tells us that whenever you have the first three, then you get a version. So this means you find another process which is almost surely identical to this one you started with, which is continuous. So, yeah. But typically, so there's no other way to do it. So it's continuous. You can include it or not. It doesn't. Please. Yes. Yes. For any kind of partition. So we'll see why this should come. This comes from the very construction of Brownian motion. So where is it? So I had a construction of the. So the first thing we will do is to construct such a Brownian motion on a fixed time interval 0, 1. And after this, we'll just glue several Brownian motions together in order to get it for the whole real line. So construction of a Brownian motion. So what we need is a family. So first of all, we need some preparations. We need a family. Please, another question? For each omega, the whole path is continuous. Yes. Yeah.
But in that set, it will be continuous everywhere.
Everywhere?
It will be continuous everywhere.
Yes, yes. So these are functions which will never have a jump. Okay, so it's really continuous so we can pick for any for almost all omegas, we can pick a continuous function with no jump nowhere. Okay, so how to construct Brownian motion? So for this, we need a sequence of functions which will generate Brownian motion. So you can write it down as analytic function, but I think sometimes the picture is much more much easier. So we have here 0, 1. Here 1/2, and we start with a function g. It will be the mother wavelet. So we call it g1 of t will be g, and this function is g. Okay, so g of t is nothing but 2t for t in 0, 1/2. And it's 1 minus 2t for t in 1/2, well, excluding here 1. Okay, so just as it is here. So the function g0 of t will be just 0. And in the next step, for any n in n, we can write down a repartition or a decomposition of n. We can always write down n as 2 to the j plus k. So the j will be the largest power of 2 which is possible to put into n. For example, let's say 9 is 2 to the 3 plus 1. Okay, and of course 8 is 2 to the 3 plus 0 for k in 0 until j minus 2 to the j minus 1. So we take powers of 2 which fit into this maximally, and then we have just some kind of remainder. So we need this. Pardon? No, this should be height 1.
Yeah, so at t equal to half, it should be 1. So it should be 2 minus 1.
Yes, okay, this could be. Okay. Okay, so having this function, we can write down gn as nothing but a rescaled version of g. It will be, so maybe the best thing is to write it, to show it as a picture. So what we will do is we will take the repartition. First of all, we have the whole interval, and then we just have two intervals. Here we have 1/2, and here we have, 1/4, and here we have 3/4. So, and here we have 1, and then we take just these kind of functions in the next generation. And in the next generation, so this is, of course, for j being 1, and then we take this kind of repartition, and so on. So we start with G1 with a constant function 1, and then we have this function, and then we have 2 of these peaks, and then we have 4 of them, etc. So G1 should be G of t. So it's G of t. It's just this function here. So we have the same thing here. So we have we construct a sequence of functions which have some interesting properties. First of all, they're continuous. This is one thing. These functions will be and 0 else. They will have just one peak, and that's it. And we have a repartition, so we just have a dyadic repartition of the interval 0, 1. And for each of those repetitions, so the generation j tells us how many of those peaks we will have are just one hat. So the G1. So G1 we have already here. This is this one. So G2 is just this function, being 0. G3 will be this one. So maybe with colors it's even easier. So this is G2. Then we have G3. Okay, and even more. Then G4 is just the next generation. We just divide it here. And G6, G2, 3, 4, 5. G5 should then be just the function, this one, etc. Okay, I think you understand how this works. The interesting thing is that in one generation, these G's have disjoint support, so beyond these points. So this means the different peaks actually don't overlap. So this is very important in each of the generations. So if you have 2 of them, one is here and one is there. If you have 4 of them here, 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 and here, they don't overlap. And this will be rather important. So what can we do? We can now construct Brownian motion in the following sense. We define a function, a sequence, lambda n, and this lambda n is equal. So we have so for each n of each, so we have the n's, and the n's define as different kinds of generations, always between the powers of 2. And lambda n will be 2 minus j half minus 1/2, I guess. Okay, so this is just a function where, once again, n is 2 to the j plus k. This means for long terms, this is always constant. So always between the powers of 2, we have constant lambda n's. So this means we define Brownian motion in the following sense. So we need a sequence zeta k. These are random variables, id, random variables, zeta k from some probability space to the real numbers. And the distribution is standard normal. Zeta k is standard normal. So we can now define Brownian motion, Bt of omega, in the following sense. It is nothing but k from 0 to infinity maybe n from 0 to infinity, lambda n times gn of t times zeta n of omega. So what we do is we sum up all those functions, but in a special way. So we have for each generations of for example, generation j, this means for power of 2 to the j until 2 to the j minus 1, we have constant functions here. This means we can understand that we have, first of all, some in the first generation, some value here. Then we have smaller values here, and then we have even smaller values here, but they're all random. They're all randomly modulated by some standard normal distribution. So we're summing up random values of these peaks. So random distortions of these peaks. So how can you understand this? You start with something. You start with a function here, and then you add first peak. The first peak is in the middle. So this is this is G1. So we have a normal distribution in G0, and then you add to this function, to this linear function, you add a function which just adds what we have there, and it adds just this peak. So going over from this to this function. And then we add the generation of the peaks which have just the peaks in the middle. So we go over from here, maybe, and there are always random values of this. For example, something like this, and then something like this. Maybe also with color. Color, here is color. So, first generation, we have some normal distribution, and then we add the first peak with a certain size, which is given by lambda 1. And then we have two additional peaks, which are, once again, modulated normally, but with a prefactor lambda n, which is a little bit smaller. So we have this, pardon. So we have this here. And this is what we are going to continue. In the next generation, we add 4 of those to each of those greens. So these are linear parts. To each of those, we add another peak. So these smaller peaks here, we add here, for example, this one, and this one, and that one. They're always little normal deviations from this already linear function, and the maximal deviation is just where the peak is maximal, and this is just where the normal distribution enters maximally. So, okay, please. Omega. So, what do we have? We have a sequence of IID random variables. This means each of the zeta k's is an argument omega. We sum up the peaks, so we have functions, GNs, which give us just replaced or displaced peaks of a certain generation between the power of 2. And then we have a new repetition of another peaks, and in each of the generation of the peaks, we have a little less impact of these normal distributions. So this means we start by construction with a linear function, and then we add here the first peak, which is a normal distribution with some prefactor. Pardon? The ZNs are just, okay, so if you have such a function, maybe I just explain it like this. If you have a function here, and you multiply it, so if this is, for example, G1, and you multiply it with zeta 1 of some omega, then of course it will not stay like this. It will be something like this, or if the value is greater than 1, it's like this. If it's negative, it can be something like this. Okay? So it's something you add different kind of multiples of these peaks. Is it clear? Are there other questions about this? Is this how the construction works? So we are always summing up all those, but where the peaks are just normally. So there's always a line. So this is in each of always in the middle of the line we have added a new peak. So the thing is, by construction of these functions, they will never overlap. Yes. Yeah, but yeah. No, but you're adding functions, you never go back in time. It's still a graph. So it remains a graph of something you cannot get two values or something like this. It's a sum of functions. It's a series, an infinite series of functions, and the functions are here actually are a random function. But this for each omega, this is not seen. It's just prefactors. So these two together for each omega are just prefactors, and you can sum them up. Yeah, please. I start with the base function, and then I make just rescaling of the base function. Here, the g's. So they are just, so the g1 is the base function, and these are nothing but rescaled version of the g. So you just... okay, yeah, okay, yeah, right, okay, yeah, sure. Okay, yeah, sure. Yeah, sure. So we have, okay, you're right. Okay, so with the linear function, and then we have the first peak, yes, okay, thank you. Yeah, you're absolutely right. So it would start on a different level, I wouldn't start in 0. Yeah. Lambda 0? Yeah, it should be, I think it should be 1. Lambda 0, so first of all, this is 0. It can be 2. Okay, we'll have to check. So it's one of those. Yeah. Yeah, but it's okay. So it's okay because of you're right. Okay, so I think it should be 1 then. Yeah. So okay, but nevertheless, okay. The main problem is not actually where the first one is, but the fact is that it converges. So okay, you're right. Okay, one should think about this. But the basic construction is always you have a linear function, then you're just adding more of those broken lines, which are just modulated in a random fashion with some prefactors, which in each of the generations are a little bit smaller. Okay, so of course, there are many things associated to this series. I would to write down only maybe one thing, just to see that it converges. And I want to show you that this converges uniform, at least on the time interval 0, 1. So if this is a series of a continuous function which converges uniformly, then the limit is also continuous. So this is the basic message. And for this, I need a certain lemma. It's not very well, first of all, this construction, well, in general, it won't converge, simply. Who was asking? Okay, so in general, it won't converge, and this construction does not work. So this is something which is, of course, you can construct such series, but the properties you get out of this are way different. You don't know what you get out of it. So this is something you use very much the Gaussian structure. So just a lemma, which is a consequence of the Borel-Cantelli lemma, which I don't want to talk about this at this stage. So if we have these zeta k's, this IID and zeta k normally distributed, standard normal distributed, then there exists a random variable c from omega on the same probability space as those, 0 to infinity, such that zeta n of omega is less or equal, maybe zeta k, in order to have it clearer, of z of omega times the square root of the logarithm of k. So this is so in the first place it looks surprising. If you have a family of standard normally distributed random variables, so in each of the points, let's say we have so maybe an equal repetition. If we have this family, so this is a random variable, so we take the absolute value of these, so we can just cut off the negative parts. So these are the values of zeta k. So for some omega, we have some value here, some value here, here, here. But you can say something about how the maximum of those will grow for more and more of them. And what this tells us is, for each omega, there exists a random function. This means which tells us how high we are, and then we know that it grows just like the function logarithm of k. So there is for p almost all omega and omega. Okay, so if we have a family of IID random variables which are standard normally distributed, and this is of course one of the cases which badly fails for other distributions. Pardon? Almost all means, without writing the omega, means almost surely. This means there is an event of probability 1, such that for all omegas in this event, this is true. But I don't specify which is the event. Okay? This event is, so this is why I was talking about the Borel-Cantelli lemma. If I would write it down, it would be the lim sup of some sequence of events. I don't want to enter this. I cannot. Without having just a week more. Okay, so, but with this, we can prove already the convergence of this series almost surely. So what we have to prove in order to get the convergence is that we have to bound for n equal m to infinity, lambda n, zeta n of omega. Maybe, okay, just don't write down the omega anymore, gn of t. So these functions are functions which have values between 0 and 1, so they are non-negative, they are bounded by 1. So this is the modulus of a standard normal distribution, and luckily enough, it's bounded by this, almost surely. And this is something which we already know. So if we can show that for m to infinity, this tends to 0, then we know that this sequence, independently of t, then we know that we have a uniform convergence of these values for t between 0 and 1. So what we have got there is, maybe I can write it down with the omegas to make it maybe clearer for those who are not committed. So for all, or p, almost all omega in omega, we have that this is less or equal, just at where we just estimate this here, then n m to infinity lambda n. Here we have the c of omega, and then we have the square root of the logarithm of n, gn of t. So this is, well, first of all, we can just plug out of the sum c, and then we go over from the summing over the n's to summing over the j's. So this is the same thing as summing over j, and the j is given as the logarithm, well, the binary logarithm of m. Okay, the corresponding j to m of 2 minus j half minus 1. And here we have the square. So having n here, we can just estimate it by the square root of j plus 1. And then we have the series over the k from 0 till 2 to the j minus 1, g of 2 to the j plus k of t. So, okay, what has happened? We've just passed from the writing of n to the writing, to the notation of this. So what we do is, instead of summing over this, we can just sum over the j's and the k's. For each of the j's, we just have to sum over the k's. So this is something, the logarithm of n is something which can be estimated due to this relation by j plus 1. Here, this is no problem. Then we have the sum over the k's still, but it doesn't enter here because the lambdas, which we have here, which do not depend on k. So they are equal for each of the generations. So what remains is that this sum only acts on those functions. Now the good thing is that those functions have disjoint support. This means for each t, only one of those functions actually strikes. We have only to sum one of them, and only one of them means that we have a function, one of those function g's here, and they can be estimated by 1. So this means this is less or equal than 1. So this is less or equal than the c of omega. Here we have the sum, from j, then the logarithm of m to infinity, 2 to the minus j half minus 1, j plus 1. And this is something which converges. This means, because, so, these functions are the functions for each generation j. We have seen that the support of those peaks is disjoint. So if we have some t here, then all the other functions of evaluated at this t are 0. So if we have this peak and we evaluate it here, then it's 0. So all of them are 0 except this one. This only one. We don't want to specify which one it is, but it's only one. And if it's only one, and we know that the peaks have values between 0 and 1, then we can estimate it by 1. Okay, so we have something, and this is finite. This is finite, and for m till infinity, this tends to 0. Okay, using this property, we get that this here, so the tail of this series, and hence this series converges almost surely uniformly. And the omegas on which this happens are the omegas on which we have this estimate. Okay, so this tells us that the construction we have here actually works as a series of random functions. Okay, beyond this, and there are quite some other properties. Okay, so we've just spent some time here. Just maybe to sum up, what we have got out of this is a random sequence of functions, a series which converges. And actually this series does not only converge almost surely, but it converges also in L2. And for this, we can show that we have the following property. First of all, we can show that this has a certain representation. It's n from 0 till infinity lambda n squared gn of t. So we can write this down, and it does exist. And what we get out is a process. First of all, it's a process which consists of sums of many independent normal distributions. So it is a Gaussian vector. It has continuous paths. We have second moments, and I won't have the time to write this down, but it is a function. Then we have that the expectation of bt is always 0, and we can find the correlation function, which is defined as the expectation of bt bs. So the expectation of this is something very well known. This is the t minimum s. So you can calculate this. I won't have the time to do it now. But what we get out is a continuous process, a Gaussian process, which is centered and which has the autocorrelation function t minimum s. So, and what we get out of this is that this is already enough to get back a Brownian motion. This is the minimum, t minimum s, yeah. And this is already enough to define a Brownian motion. This means we have a Gaussian vector, and we can calculate the increments. So first of all, we can, with a Gaussian vector, we can calculate the increments. Let's say, so if we have a Gaussian vector, and we want to see if the increments bt1, bt2 minus bt1, btn minus 1 are independent. We already know this is a Gaussian vector, so the only thing we have to check is that they're uncorrelated. So this is a big benefit of this construction, which is absolutely not possible for non-Gaussians. So we can actually check it. So pardon, bti minus 1, btj minus btj minus 1. In the case of that, without loss of generality, bti is less or equal than btj minus 1. And here we have ti minus 1, and here we have tj. Okay, so in this case, so we can just multiply it, and we get something of this shape. And so we have here the expectation of bti, btj, minus the expectation of bti, btj minus 1, minus bt, once again, the expectation bti minus 1, btj, plus the expectation of bt I minus 1, bt j minus 1. So we've reduced everything to the function c we have got there, and with the assumption that one of those is smaller one, the smaller one, we just get that this is nothing but 0 if they're different. Because here we have seen that we have non-overlapping time intervals. This means those increments cannot be equal. So, and what we get out of this is just 0. You can just check it, that here we have ti, here we have, if we have ti less, ti, here we have ti minus ti, minus, here we have tj minus 1 plus tj minus 1. So this is actually, this sums up to 0. So we have the independence of the increments with a Gaussian vector, and this is actually enough to get back a Brownian motion. Hence, what we have seen, okay, shortly, but we have seen that bt with this construction is a Brownian motion. So the important thing is, one moment, we have constructed with this random series a process which starts in 0, which has independent increments, which has normal distributions and almost surely continuous paths. This by construction of this random sequence, and this is by the Gaussianity, just summing up so many independent random variables. Now, please. Yeah. Because we're summing up, this is just summing up. Yeah. Yeah, but Gaussianity of the vector means that you only take finitely many points. Yeah. Yes. Okay, so in general, you're right. There could be an issue, but in this case, it's not. So okay, we can talk about this in the tutorial and afterward, just to make it. But it's no problem at all. It's Gaussian, and it's a Gaussian vector which has just the autocorrelation function just given by the minimum. All right, I think it's over. Thank you very much. Questions? The Lévy process, what we get out is we have almost the same thing. We drop the continuity, we replace continuity by right continuity, and we drop that we have a Gaussian here. We will write something infinitely divisible, and that's enough. This will be, in the end, the Lévy process. The next time, so I could not finish actually the Compas-Poisson process. We'll talk about this, I think it will be Saturday. In general, so Lévy processes in general are generalizations of Brownian motion where we don't have the Gaussianity, we only have replaced it by infinitely divisibility, and we will see, or I will just try to motivate why we cannot have continuity. This will be processes which have naturally jumps, they have continuous parts, and they will have almost the same components as we have seen in the Lévy-Khinchin theorem. This means a linear drift, a Gaussian part which will correspond to the Brownian motion, to a Brownian motion. There are different kinds of Brownian motions, and a jump process which is once again the sum of something like a Compas-Poisson random variable or process, and a process which is has to do with this explosion of the Lévy measure around 0, which is a jump process with bounded jumps, but infinite intensity. This will be the story to follow next time. More questions, please. Yeah. Yeah. Oh, there are many ways to define Brownian motions. So this is, first of all, you can change the base function. So historically, by Paul Lévy, it was just some sine cosine functions, which are also perfectly possible. This is the easiest way because here we have this disjoint support, which helps us to get rid of such a big sum. Otherwise, if other base functions are simply, so there's a long evolution of constructing Brownian motions, and I think this is maybe the shortest and neatest way. Otherwise, if you have, so the first articles about this were very long, just estimating why this should converge. More questions? Okay.